Stripping down science. The Naked Scientists.
Hello, it's Sunday the 12th of February in 2012. Welcome to The Naked Scientists. I'm Chris Smith, and with me this week is Kat Arney. Hello, Kat.
Hello.
And this week we're looking at the tech that could turn waste heat into electricity and what that could mean for the automotive as well as the energy and space industries.
And in the news, we'll hear how disguising cancer cells as salmonella could hold the key to producing anti-cancer vaccines, and a new drug that could knock the cause of Alzheimer's on the head.
So, if you have any questions or comments for us, tweet at Naked Scientists. You can also write on our Facebook page, which is at facebook.com/TheNakedScientists. Or you can, of course, drop us an email. Our email address is chris@thenakedscientist.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Now, incredible as it sounds, over 70% of the energy released when you burn the fuel in your car gets wasted, and most of it flows out of the exhaust pipe in the form of heat that we then throw away. And with average oil prices higher than they've ever been, researchers are looking for ways to scavenge back some of that wasted energy to make some efficiency savings. The approach they're taking is to use thermoelectric generators, or TEGs, that can turn heat into electricity. And this is something that the UK's National Physical Laboratory, NPL, at Teddington, is pioneering. And one of their scientists, Laurie Winklis, works on this technology. Hello, Laurie. Welcome to the show.
Hi, Chris. Thank you.
So how do these devices work?
Basically, a thermoelectric generator is based on a semiconductor material. It's sandwiched in between two pieces of ceramic with some electrical conductive material, maybe copper, in between. They effectively work by having a temperature gradient applied to the device. And the bigger the temperature gradient, the more of a push that the charges in these materials get. So inside the semiconductor, you have a positive charge and a negative charge. So you have an electron, which is the negative charge, and you also have something called holes, which act as a positive charge. When you apply a temperature gradient to one of these devices, you give energy to the charge carriers, so both the electrons and holes inside the material, and it causes an electrical flow in the device. And when you add up several of these couples together, you get a very nice, very reliable force of electricity.
This physics sounds very cutting edge, but it isn't new, is it?
Not at all. Actually, the first thermoelectric effects were discovered and described beautifully in the 1800s. So we've known about the theory for a long time. They've been used in the space industry probably since the 50s or 60s. But now down on Earth, we're starting to look into using them in a much more realistic way in the last probably 10 to 15 years.
So what's the difference between what the physicists of yesteryear in the 1800s would have done and what we're trying to do today?
Well, back in the 1800s, there was no information on semiconductor materials, for example. Everything was either an insulator or a conductor. Semiconductors are a relatively recent phenomenon. Of course, we take them for granted. They're in every piece of electronics in our house. But the discovery of semiconductors and the application of those equations from the 1800s have led to a new way of producing electricity from a temperature gradient from heat.
So those early scientists were pretty clever, and they worked out there would be an effect. They worked out this was theoretically possible and would produce very tiny voltages for them. But with the application of modern materials and modern engineering, we're in a position to produce actually meaningful voltages that could do something.
Yes, indeed. They described the effect for a metal, for example. So you get a very, very tiny voltage. In semiconductors, you get exactly that, a much more useful voltage that we can do something with.
So how are we actually trying to do that then?
Well, at the National Physical Laboratory, our focus is on trying to understand the measurement around these materials. I always say to people, describing how these devices work is like trying to measure mass without knowing what the kilogram is. So we need to have that kind of measurement standard in place. So there are actually a huge number of applications for these devices, and the space industry being probably the one that's most established, where they're used as a power source for deep space missions and beyond. The power plant industry are starting to catch up, and the car industry are the ones who are most recently investing quite a lot of money in looking into using these materials and devices.
Because if I really am throwing away 70% of the energy in my fuel tank, that's a lot of money. It stands to reason then that if I take all the hot parts of the engine, and especially the exhaust, I ought to be able to get that energy back using one of these devices and turn it into an electrical flow that I could do something useful with. How much of a saving do you think I could make were I to implement this on my car today?
So there are quite advanced prototypes by Ford and BMW, for example, which have quite high wattages, but I haven't seen enough evidence to quote them to you. But 5 years ago, they put one of these tags, actually based an entire tag system around the exhaust, so capturing all of the heat that's in the exhaust up to 500 degrees in this particular car. And they ran the car along a motorway, and they produced about 500 watts of power, which equates to about a 5% saving in fuel.
Which could save you quite a lot of money, couldn't it, in the long run?
Well, yeah, in the long run, it's worth looking into at least. The devices themselves aren't amazingly efficient yet. We have a lot more work to do to make them incredibly efficient. But already you can see a saving, and you can see the improvement in the efficiency of the system of the car.
These things would flank the exhaust pipe or whatever heat source there was. So that's the hot side. You're giving the particles, these electrons and the holes, energy on the hot side. How do you then get them to move towards that cold side? How do you make the cold side to create the current flow? The
dream would be that you just use the airflow of the car moving down the motorway, for example. But the reality is it's not a very reliable cold source. So what car industry particularly are trying to use is the cooling system that already exists in the car. So it's generally something like ethylene glycol, and they just reroute the cooling system to wrap around the tags, and that produces the cold side.
And what sorts of materials, because you said semiconductors quite generically, but what sorts of semiconductors, what are the materials that we're using that are bearing fruit in this regard?
On the kind of what I would consider lower temperature levels, so around 200 degrees Celsius, you have the quite exotic sounding bismuth telluride, which is a semiconductor device which at that temperature has an efficiency, a thermoelectric efficiency of maybe 5-7%, not a huge efficiency. But as the temperature variation increases, so as you have a much hotter side versus a cold side, when you have maybe up to 500 degrees plus, you have to start looking at different materials, because bismuth telluride is not great at those temperatures. You start to look at things like silicon, germanium based, so materials we're actually quite familiar with already as they're used in the electronics industry.
And critically, what about the cost of those materials? Are they readily available and fairly cheap, or are we looking at a major price hike to save 5 pence on a litre of fuel?
Well, bismuth telluride ones are actually extremely cheap, surprisingly cheap. You can get these tags, so bismuth telluride tags, which will produce about 100 watts for about £90. So about £1 a watt is generally quoted.
Cheaper than a catalytic converter, isn't it, at the moment, which is ridiculously expensive?
Yeah, indeed. But when you get to the higher temperatures, the materials get a little bit more exotic, so the price will increase accordingly.
Now, help me out with one frustration, which is that if you have something that conducts electricity very well, it conducts heat very well, because the electrons are jiggling around and they then move through the material, making other things jiggle around. That's how heat transfers. So how do you get this efficiency then, where you have something which will let the electricity flow, the electrons, but keep the heat back? It sounds like a paradox.
Yeah, it is indeed a paradox, and it's actually a measurement issue too. If we want to know exactly how much electricity can flow through these materials, we need to know its electrical conductivity. We need to know it very accurately. We also need to know its thermal conductivity, how happy it is to allow heat to flow through. So to measure one and not the other is actually extremely difficult. They're coupled together quite strongly. But one of the efforts, and this is kind of on a research level, is to look at nanostructuring the material. So actually changing the material, its shape on the nanoscale, to increase the number of barriers or interfaces that the heat and the electrons have to flow through. Electrons are pretty happy to bump their way through interfaces. Heat takes a bit more of a beating, so it slows down the heat flow through the material.
So you can make a material which will allow electrons through, but will frustrate the progression of heat through the material, and therefore you can maintain a hot side and a cold side and drive that current.
Yeah, you can to a degree. Of course, we are subject to the laws of thermodynamics like everyone else, unfortunately. But yeah, the idea is that you keep the temperature gradient for as long as you possibly can. You will always get hot and cold giving you warm at some point, and you start to lose power output at that point, but you can then cool the whole tag down and restart the flow.
Love the pun on to a degree too. Well done, Laurie. Laurie Winklis from the National Physical Laboratory.
And if you want a bit more background on TEGs and how they work, there's a fantastic little vignette in the latest science scrapbook video that's available now at thenakedscientist.com/scrapbook.
And Laurie is actually with us for the rest of the programme. So if you've got any questions on the technology she has been discussing, get in touch now. You can tweet at Naked Scientist. There's also facebook.com/thenakedscientist for our Facebook page. Our email address, chris@thenakedscientist.com. Kat.
So we've heard how thermoelectric generators, or TEGs, could be a useful way to turn waste heat energy back into useful electricity in small-scale settings like cars and things like that. But there are also settings on the very big scale, for example like a power station, which throws away huge amounts of heat up its cooling tower. So could thermoelectric technology help here? Now, we're going to talk now to Andrew Knox. He's Professor of Power Electronics, Renewable and Sustainable Energy at Glasgow University, and he's looking at the feasibility of using this kind of technology, but more or less in reverse. So good evening, Andrew.
Good evening, Kat.
So tell me a little bit about, for a start, the kind of scale of heat loss we're talking about in a power station and why it would be attractive to try and use thermoelectric technology.
Much of the UK's power generation comes from what's called thermal power stations, and that's whereabouts we burn fossil fuels, gas, coal, etc. And the generation of electricity from that process is subject to various thermodynamic restrictions. And it's the same basic problem that the thermoelectrics have got, where you've got a hot and a cold side, and the maximum efficiency is a function of those as determined by the Carnot cycle. In a conventional thermal power station, typically what happens is you burn the fuel, let's say coal for example, that raises steam in a boiler. That steam is then routed through a turbine, and the force of the steam going through the turbine turns an electrical alternator, which is what generates electricity. The steam goes through a series of different turbines, each at progressively lower pressures, and at the end of that process, when you've extracted about as much of the useful work as you can out of the steam, what you have to do is recondense the steam back into water, and that water is then returned to the boiler to be used again. And the water that's used for this as the working fluid for this power generation process is exceptionally pure. And the reason for that is that any impurities that would be in the normal tap water, for example, would convert your turbines into Swiss cheese very quickly. I mean, it would really attack the turbine blades. So this process that's going on of boiling water, driving it through a turbine and then condensing it back to water and reboiling it back in the boiler, that process is called the Rankine cycle, and it's subject to limitations. Now, if you drive past a large thermal power station, let's take, for example, Ferry Bridge down the M1, which is a sort of fairly well-known route. When it's working, you will see large quantities of steam being rejected from the cooling towers, and the cooling towers are these big, huge concrete structures, and that's basically dropping the energy out of the steam back to the environment. So that's wasted heat. And on the best modern thermal power stations, their efficiency is about 47%. So more than half of the energy that's used is being rejected to the environment.
So in a power station, we have a lot of things that are very hot and things that you're trying to cool down. So there does seem to be capacity to use thermoelectric technology. But you're proposing a slightly different way, not using the difference between heat and cold to generate electricity, but something else. How would you introduce, or how do you think we could introduce thermoelectric technology into a power station to make it more efficient?
Yes. One of the things that Laurie touched on is the semiconductor thermoelectric generators. One of the properties of these thermoelectric generators is that, as Laurie described it, if you apply a temperature difference, then you will generate a voltage from them. But if you apply a voltage to the same material, the same device, you can actually use it to shift heat from one side to the other. And in the context of the power station, in the condenser of the power station, whereabouts the used steam is converted back into water, as that steam gives up its energy and condenses the latent heat of evaporation, by using thermoelectrics, we can actually capture some of that energy and re-inject it back into the power plant rather than rejecting it to the atmosphere.
So you're talking about actually taking the heat and putting the heat back into the system to generate a bit more electricity again?
Yes, it's very low-grade heat, but it's more sort of conceptually thought about as the energy released as the steam gets converted back into water.
So this would mean
enthalpy.
So this would mean you'd basically get kind of more bang for your buck. So for the amount of coal that you're burning, you would end up getting more electricity out the other end.
correct. You would end up having to burn less coal for a given amount of electrical output from your generators.
So this sounds brilliant, but how realistic is it? What are some of the challenges that are there to try and implement this kind of technology?
There are two challenges, or there are many challenges. There are two big challenges. The first one is the engineering of the condenser itself. In other words, you need to get tens of thousands of these semiconductor devices properly arranged in the steam flow to maximise the heat transfer. And the second thing is to optimise the electronics that would be used to drive this process, because the Peltier effect, as it's called, which is the sort of property of this semiconductor material when it's in use like this, that has what's called a coefficient of performance, and that is determined by the difference in temperature between the hot and the cold side. And in general, as the coefficient of performance, as the temperature difference increases, the coefficient of performance decreases. So this is not something you can use up to whatever temperature you like. This is really to be used only at the low temperature. And for a typical large-scale power plant, the steam coming out of the last stage of the turbine is about 35 degrees C.
So do you think the kind of technologies you're talking about could actually be fitted into the power stations we have now, or will it take a new breed of power station?
No, I think it's suitable for both new build and for retrofit. I mean, the efficiency is such, using today's devices with today's materials, that we have just about, or we're at the break-even point. There's two contributing factors which help us here. One is the power station efficiency itself. As we go to all these supercritical, very high temperature, very high pressure steam, that helps us. And also, as the materials in the semiconductor devices improve, that also helps the overall efficiency of the heat pumping and therefore the coefficient of performance of the heat pump.
And do you think, I mean, I know this is kind of a how long is a piece of string question, but if all the research goes well, when do you think this kind of technology might be able to be brought in?
I would think you're probably looking at 10 years. To do a large-scale power station, or like Ferry Bridge or DRAC, something like that, that would be ambitious, to say the least. But if you were to go for a sort of relatively modest, say a 1 megawatt to a 5 megawatt power station, then I would expect to see in 10 years' time that will be available, modified Rankine cycle.
And you think the benefits that could be gained in efficiency and saving money on coal would actually make it worth investing in this kind of technology?
Yes, I do, because even if you're only talking about a couple of % efficiency increase in the overall coal to electricity conversion, that couple of % represents a huge amount of power if you take it over the lifetime of the power station of maybe 25 years, coupled to the fact that energy prices are going to continue to increase, in my view.
So that's definitely something worth investigating and investing in. Thank you very much, Andrew. That's Professor Andrew Knox from Glasgow University.
Keeping you abreast of the world's best science. The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and with Kat Arney. We'll return to this week's topic of thermoelectric generation and find out in a minute how they're helping us to go where no one has gone before. But before then, let's take a look at what's hitting the science headlines this week. Kat, what have you got for us?
Well, here's an interesting one from The Lancet this week. Although deaths from heart disease are falling, it is still a major killer in the UK and other countries around the world, and men are more likely to suffer coronary heart disease than women of the same age. Now, this has often been put down to chaps having an unhealthy lifestyle, drinking, smoking, sitting around watching Match of the Day and eating pies. Obviously, slight generalisation there. But an international team of scientists in Leicester has just published a paper in The Lancet showing that there may actually be a genetic component at work.
So this has to be related to the sex chromosomes, presumably, because you're seeing this male-female dichotomy.
Absolutely. Now, although men and women share almost all the same genes, there's one important difference, as you point out. Women have 2 X chromosomes and men have an X and a Y. Now, there's only a handful of genes on the Y chromosome. It makes around 27 individual proteins, and most of these are thought to be important for sexual development, making men manly. But in recent years, there's been some intriguing links made between this tiny little genetic estate and diseases including HIV and autism. So the scientists decided to analyse the genetic makeup of the Y chromosome in more than 3,000 British men that were involved in 3 different heart disease studies here in the UK. Now, because Y chromosomes are passed down almost wholesale from father to son, with very little genetic muddling from generation to generation, there's only a limited number of different flavours, or haplogroups, as scientists call them, of Y chromosomes. And because of this, the Y chromosome is actually usually left out of most large-scale genetic studies that look for links between genes and diseases. But in this case, the researchers found that all the men in their study fell into just 9 haplogroups, and 90% of the Y chromosomes came from just 2 different haplogroups. And when they looked at these men and their history of heart disease, they found that men with Y chromosomes from one particular group, this so-called Group 1, had a 50% increased risk of developing coronary heart disease than men whose Y chromosomes came from the other haplogroups.
Roughly, Kat, do you know what fraction of the total had that particular risk factor?
Well, it's probably a significant number of men, because 90% of the men they looked at had these 2 different groups, so it's probably quite a big number of men who would carry this risk factor. But they did think, after a bit more digging, they confirmed that this association wasn't just linked to other risk factors for heart disease, such as lifestyle factors like drinking and smoking or other known biological risk factors. And then when they looked closer at the activity patterns of genes in men from these different haplogroups, they found clear differences between those in the high-risk group and other groups in the activity levels of certain genes involved in inflammation and autoimmune responses. And now we know that both of these are quite important in heart disease.
Indeed. So where do they say we should go from here?
Well, at the moment, this is just an association, although it is the first study to actually robustly uncover an association like this between heart disease and the Y chromosome. Now, a lot more work needs to be done to confirm this and figure out exactly which genes on the Y chromosome are involved in this, but in the future it could help to lead to new ways to reduce the risk of heart disease, or even maybe treat it. And also, because the Y chromosome is passed down wholesale from fathers to sons, it also tells us that in some cases susceptibility to heart disease may actually be inherited in this way.
Intriguing. Thank you very much, Kat. Now, you've heard the saying, feed a cold to starve a fever. Well, maybe we also need a saying, feed a cold and starve a cancer. There's a paper that's published in the journal Science Translational Medicine this week. It's by Walter Longo, who's a researcher at the University of Southern California. Now, they started off using yeast cells, which they'd added a cancer-causing gene to, and showed that if you deprived these yeast cells of food for a while, then the cells that have got the cancer gene in show signs of intense stress, whereas the cells which are normal, they sort of switch down their metabolism and put themselves into a protected state. They then repeated the experiment with normal cells and cancer cells in the dish and got the same result. Then they went to actual physical cancers in mice. They had mice with breast cancers, melanomas and gliomas. They're a kind of brain cancer. And in these individuals, they find again, if you fast the animal and then give it a dose of chemotherapy about 60 hours later, and then wait 24 hours and then have normal feeding again, animals that get treated like this have a much greater response to the chemotherapy compared with animals that are normally fed throughout. And the animals don't lose lots of weight, which is an important consideration in cancer, because they're only fasting for a short period of time. But it does appear that doing this dramatically increases the sensitivity of cancer cells to chemotherapy. And in fact, the numbers on this, in the mice they studied with melanomas, they had 40% fewer cases of metastasis or spread of the cancer in these mice that were fasted, and they had 42% of the animals having long-term survival compared with 100% mortality in the unfasted group. They think that the mechanism could be down to the fact that the cancer cells, by definition of being a cancer cell, grow very aggressively all the time, and they lack the ability to have a cellular off switch. So when they're placed in a stressful environment, they cannot switch themselves off, and so they relentlessly carry on trying to grow, with the consequence they become very stressed and therefore much more susceptible and vulnerable to the chemotherapy.
I think that's really interesting, because there's so much more we need to really understand about the metabolism of cancer cells and how it's different from healthy cells. So that does sound interesting, but it does need to be stressed at the moment that this doesn't tell us that human cancer patients should be fasting or starving themselves in any kind of way, because I think a lot more does need to be done to try and understand this effect.
We're sticking with cancer. Making cancer cells resemble the Salmonella bacterium might sound like an odd thing to do, but funnily enough, it could hold the key to creating anti-cancer vaccines to trigger the immune system to actually attack cancers. And to explain how, we're joined by Professor Julie Megarian-Blander from the Mount Sinai School of Medicine in New York. Hello, Julie.
Hello.
So, first of all, tell us, why doesn't the immune system attack cancer in the first place?
The immune system recognizes its own tissues by a process called pattern recognition. So when it's searching for microbes, it's really searching for patterns that are associated with microorganisms. And these patterns are absent from normal, healthy tissues. And therefore, because tumor cells and cancerous cells are derived from normal cells, they don't have those microbial patterns that the immune system likes to see and target.
So that's why they escape normal surveillance. So what were you doing with Salmonella?
With Salmonella, there is this protein called flagellin, which Salmonella and other bacteria actually use for locomotion. And therefore, we took this protein, the sequence of this protein. It's easy to express in cells because it's a protein in nature. And we expressed it in tumor cells in order to make them look more microbial to the immune system. By doing so, we could target the receptors that recognize these patterns or structures that are associated specifically with microbes. In this way, you're tricking the immune system to think that tumor cells are actually have a component that's derived from microbes, and then they're targeted this way.
So the cells are made to look more like a bacterium. This gets the interest of the immune system via these special receptors it has to pick up pathogens. The immune system then attacks the tumour cells. That's all very well for the tumour cells that you have added the Salmonella-like gene to, but what about the rest of the tumours elsewhere around the body?
So the strategy is used, the way we did this in animal models, in mice, the strategy is to take the tumor cell itself, introduce this flagellin protein in order to target the receptors of the immune system, and then irradiate the tumor cell and use that as a whole cell cancer vaccine. So the animals, we have done two different sets of experiments where animals that do not have tumors have been vaccinated, and then we tested their protection against subsequent challenge from a wild-type tumor that does not express the flagellin. And then we've also done experiments where animals that bear tumor already were vaccinated, and then we monitored the immune response. And in both cases, we were able to see that the immune system efficiently mounts a robust immune response, both a CD8 cytotoxic T cell response and a helper response that's important for making those CD8 T cells aggressive and capable of attacking the tumor cells.
So the immune system, once it's been primed using the Salmonella-resembling vaccine cells, which are actually killed and don't go anywhere else once you put them in, the system then begins to attack the rest of the tumour. Presumably there's some kind of crossover then. The immune system learns to recognise the cancer cells having had its interest piqued by the presence of the Salmonella flagellin gene.
Yes, exactly. Because what we were able to show is that we can boost the memory response. Because vaccination, the whole basis for vaccination for infectious diseases is, for example, you vaccinate with a particular component of a microbe, and then that individual that's been vaccinated is protected for their sometimes throughout their lifetime against the infection itself. And so here it's the same idea. Because the microorganism has been seen, the flagellin from the microbial components from Salmonella is seen within tumor cells. The immune system can then make a response to that tumor, and then subsequently that memory response is what protects against further development of or growth of the tumor.
And there's no danger that the immune system might be led to start attacking healthy tissue because it gets interested in the cells and reacts to the wrong thing on them and then starts taking down healthy tissue?
Yes, this has been a caveat for whole cell cancer vaccines, and many investigators do not prefer that. But there are also powerful mechanisms of tolerance that are inherent to the immune system, and those mechanisms we have not addressed this in our study, but those mechanisms are so powerful that we think that we might be favoring the presentation of specific cancer-derived molecules. And those are the ones that are preferentially going to be targeted. So cancer cells can share normal proteins with healthy cells, but they also have their own set of proteins that they express, and there's a lot of effort in identifying what those proteins are. So our hope is that by introducing flagellin, we can bypass the process of systematically identifying the individual proteins that cancer cells might have unique to them and not expressed on normal cells. In this way, we could, without knowing what those specific proteins are, we could prime the immune system to a whole slew of things that are going to be new to the immune system. And therefore, those normal proteins may not be targeted, but it is something that we need to test in animals.
And just to finish off, talking of animals, the mice that you tested in your study, how did they do? What sort of improvement or clinical outcome did you get with those animals that were treated with this vaccine?
We had several models where we had transplantable lymphoma cells and also melanoma cells that are metastatic. The melanoma cells, it was really dramatic because these melanoma cells are injected intravenously into mice and they metastasize to the lung. Those mice that were vaccinated with the flagellin-containing melanoma whole cell vaccine did not have any metastases. Their lungs were completely free of metastases compared to the control animals that were not vaccinated. And similarly, the subcutaneous growth of those tumors, lymphoma cells that we had transplanted subcutaneously into the immunized mice, all the mice rejected the tumor and were capable of mounting a robust memory response to that tumor compared to the wild-type unimmunized controls.
Super. We'll leave it there, but thank you for bringing us up to speed. That's Julie Megarian-Blander from the Mount Sinai School of Medicine in New York. She published that work this week in the journal Science Translational Medicine. On to Alzheimer's now, and a new drug that could potentially help to alleviate the condition. This is an agent called targetin, or its generic name is bexarotene. This is a molecule which activates what's called the retinoid X receptor, which is involved in triggering various genes to be turned on and off in cells. It was originally licensed for the control of a disease called cutaneous T-cell lymphoma, but has also been used subsequently for other malignancies, including breast cancers and skin cancers. What a group at Case Western Reserve University, led by Gary Landreth, are publishing in the journal Science this week, though, is evidence that it may be able to dissolve the pathological proteins, the beta-amyloid plaques that build up in the brains of people who have Alzheimer's disease, and in this case in experimental mice, which have been genetically programmed to develop the rodent equivalent of Alzheimer's. What the drug does is it activates these RXR, retinoid X receptors, in cells, and this leads to the expression of a gene called ApoE, and this can dissolve these beta-amyloid plaques in the brain. And what the team found is that animals given this agent immediately reduced by 25% the amount of A-beta, the pathological protein that you can detect in the fluid around brain cells, and if you give animals a 14-day treatment of this agent, then the number of plaques in their brains decreases by up to 75%. And if you look at older animals that would by then have had quite severe Alzheimer-type change in their brain, you see a 50% reduction in the plaques. This is also borne out by functional improvements because the treated animals maintain their cognition and their faculties much better compared with untreated animals. In tests of sense of smell, which is lost in these animals, they perform much better than controls, and they also show more normal things like navigation behaviour and nesting behaviours too. So this suggests that if we could do the same thing in humans and try this agent, which is already licensed for treatment in humans, on people who have Alzheimer's disease, we may see a similar benefit, because previous trials that have actually used vaccines to make the immune system remove these beta-amyloid plaques did result in people developing cognitive benefits. So using this agent to do much the same thing suggests there could be a lot of promise in doing this.
Yeah, I was going to say, because the drug's already licensed, that should be quite a strong indicator that it should go into trial fairly fast, I would hope. Anyway, now moving on to something completely different. A new project launched in London this week ahead of the 2012 Olympics to get school children across the country thinking about their bodies and how they work, using sports, exercise and a range of scientific experiments. Mira St. Fillingham went along to the launch.
The pupils of St Paul's Trust School in East London were treated this week to a range of experimental kits, helping them to explore the inner workings of their bodies during exercise. The kits will be delivered to schools across the UK as part of an initiative inspired by the 2012 Olympics and brought in by the Wellcome Trust to help pupils get active and in the zone, as Mark Walpott, director of the Wellcome Trust, explained.
The Wellcome Trust has launched a series of kits for schools called In the Zone, teaching the next generation about their bodies and fitness, which is designed for all stages of schools, so it'll go out to more than 23,000 primary schools, to more than 6,000 secondary schools. And each of the boxes contains a series of experiments.
So it's really focusing in perhaps on physiological traits that would benefit people perhaps during exercise?
Yes, that's part of it, and it's also partly about teaching people how their body responds to exercise. And so if you think about the brain, reaction time is important. So there is an experiment that can measure reaction time. Your muscles are obviously hugely important in exercise. And so for primary children, there are simple experiments like, can you jump further if you have longer limbs? For secondary schools, we've got experiments that teach people about lung capacity. Obviously, if you have big lungs, you're much fitter potentially. Your heart rate is a very good measure of your fitness and how your heart rate changes in exercise. And so we've got pulse oximeters. And so it's a whole series of experiments which are, on the one hand, linked to the curriculum, so they're relevant to science. On the other hand, they're specifically about health and exercise.
Have you had a go on much of the equipment yourself?
Yes, I've had a go on some of it, but I'm not sure I'd like to tell you the results.
Wellcome Trust Director Mark Walpott. And although Mark wasn't keen to share his results, many students were, as they publicly performed some of the experiments out on display, including one measuring lung capacity.
Hi, I'm Kulsuma Begum. I'm 13 and I'm in year 9.
So, Kulsuma, you've got a particular one of the experiments from the kits here, which is a long plastic bag, essentially, with lots of numbers down it.
Basically, it's got litres on the bag. You have to blow in it, and that will show you, if you like, how much you can breathe into it with your lungs and everything.
So this looks at your lung capacity?
Yeah, lung capacity. It's to do with your height, whether if you're longer, will you blow harder, or whether if you're shorter, you will blow lower. So that depends on that.
Okay, so how tall are you?
Me, I'm 5'3".
Okay, so let's see how much air you can let out.
Okay, I'll try it then.
So you've breathed out a litre and a half?
Yeah.
One man able to fill the entire 6 litres of the bag and more was 5-time Olympic gold medalist Steve Redgrave. Though he is 6'4", and the kits help you learn that height can greatly benefit this particular physiological attribute.
Hi, I'm Steve Redgrave and here with the Wellcome Trust today at having a lot of fun doing some experiments.
What would you say are the main physiological traits that people need to succeed at rowing?
The physical side is the length of levers. You don't really get very small people doing the highest level. You can get short people to a reasonable level, but when it actually comes down to the elite side, they're all very tall. It's all about long, lean levers in some ways.
Being tall is good. You've got those levers to get you through the water quite quickly. But what about your internal, say, organs?
Well, rowing is an endurance-based sport. So, yeah, you've got the physical side, you've got the right specimens of leverage-wise, is that now they've got to be trained to be able to be very efficient. If you don't have the lung capacity, the VO2 uptake, of transferring that oxygen into energy that goes into the red blood cells to feed the muscles from that point of view, is you're not going to be very efficient from that way. So the science behind it becomes immense. Training, preparation, monitoring of trying to improve levels all the time. When I started back in the 70s, there was none of this. I remember one of the chief coaches wanting to do a muscle biopsy on me. I'd worked for a number of years building up my muscle, and they want to stick a little needle in and pull a bit out just to find out if I was a fast twitch or slow twitch fibres. Endurance sport tends to be more low twitch, speed tends to be more fast twitch. I was a reasonable sprinter, so I must have a reasonable amount of fast twitch fibres within my makeup. But endurance-wise, you can train it. So having that ability of natural speed and then train endurance-wise, so the best of both worlds in some ways.
Did you learn a lot about how your body actually works through all this training and through all this scientific kind of methodology? And did that help you then to get better?
Yeah, no, I think it does. Sport, everyone seems to get faster all the time. They may not get faster every time they go out or within a year or even an Olympiad of the 4-year cycle. But over a period of time, times get quicker, athletes get quicker. So you've got to use every aspect. So of diet, training, the science behind it all plays a part of being a better and faster athlete than we were before.
That was Olympic rowing champion Steve Redgrave, and before him, Wellcome Trust Director Mark Walpott, and both were talking to Mira Senthilingham. If you'd like to follow up on any of the news stories we've covered this week, the stories and references are available at thenakedscientist.com/news.
Rivers in cities and towns have had a rough time over the years. They're often diverted, hidden, or even lined with concrete, and some even end up as sewers. But now, around the world, urban rivers are undergoing a revival, many becoming havens for wildlife in the process. And Planet Earth podcast presenter Richard Hollingham has been to visit a project in South London where conservation science is helping to turn a long-neglected river into what's very much an urban asset.
I'm in Carshalton near Croydon in southwest London. 200 years ago, this was a rural village. Now it's part of the vast suburbs encircling London. The river at its centre, the Wandle, once flowed through fields of crops. Now it's surrounded by roads, railways, houses and businesses. And rivers in places like this often end up neglected, polluted and unloved.
A couple of 100 years ago, this area was much more rural.
Bella Davis from the Wandle Trust.
The river had already been impounded by lots of mills. It's actually known as one of the hardest worked rivers in the world for its size. And moving forward from them, we had the Industrial Revolution and there was an awful lot of pollution went in. General disregard for rivers across the country. By the 1960s, it was an open sewer and more or less biologically dead. Through the 70s, it got very canalised and made very straight to help with flood defence issues. And then rolling forward to now, we're trying to restore many of the natural processes and natural habitats that would have been there.
The Trust has used the expertise of Angela Gurnell from Queen Mary, University of London. Her research has found that even rivers lined by concrete, covered with bridges or interrupted by weirs are still worth saving.
The surprising finding we had was that actually certain types of engineering are compatible with quite a varied and aesthetically pleasing, and if the water quality is good, quite a strong sort of ecological functioning of these rivers.
So really all is not lost, even if it's surrounded by concrete and in an urban area?
Increasingly, there's opportunities in situations like this, where we're standing, where the river's confined on one side by a road, on the other side by housing, and above us by a railway bridge. You can still do quite a lot to improve that section by just gently pushing away at the engineering and removing the bits that you actually don't need, and allowing the river to recover in a patchy way.
And what we did was to knock out part of the weir and to channel the water through that, so the same volume of water is going through a smaller space, so it's going much faster, as it would more naturally. We've introduced about 60 tonnes of gravel through this area, and we've sculpted that so it has a range of different habitats within that, different morphology to it. We've narrowed the river upstream and put in place new banks, taken out some of the silt that was held behind the weir, and we've put in over the top over 1,000 native plants.
And that's meant the Wandle not only looks much more natural, but it's seen the return of fish and the birds that feed on them, like the kingfisher. But further upstream, the river's disappeared completely. In a park near the centre of Croydon, I met up with Tom Sweeney from Croydon Council.
In 1967, the council culverted the river. It was buried underground, but in a few weeks' time we will have the signs of the River Wandle sort of re-emerging in the park.
So where is it?
We're standing on top of it at the moment.
OK, so point out, we're on a slightly muddy area of the field here.
We have some red lines over here which denote where we're going to put the new headwall structure for the river. And it then stretches back towards the centre of Croydon, through the middle of that open field there to the other end of the park.
So you're essentially turning a pipe back into a river?
Yes.
And as we watched, a digger began scraping away at the earth to reveal the top of the culvert and the long-forgotten waterway. Angela Gurnell.
By opening up these culverted sections, we connect the sections of river back together again, and that's fantastic from an ecological point of view because it allows the species to move up and down the system.
Waterways in towns and cities may never return to their former glory, free to meander through the landscape, untouched by civilization. But a few changes, backed by scientific expertise, are transforming them back into corridors for wildlife.
Planet Earth podcast presenter Richard Hollingham. And you can hear more about urban rivers in the latest Planet Earth podcast, which you can find at the Naked Scientist website, nakedscientist.com/planetearth.
Distilling the best science. The Naked Scientists.
And you're listening to The Naked Scientists. We're looking this week at the concept of thermoelectric generators with Dr. Chris and Dr. Kat. Now, powering spacecraft is a challenge. Traditional chemical-based batteries, well, they go flat, and for deeper space explorations where the sun don't shine, solar power's out of the question. Instead, the European Space Agency are working on units that rely on radioactivity to provide the heat needed to run a thermoelectric generator. Dr. Richard Ambrosi is from the Space Research Centre at the University of Leicester, where he does the work that helps to power our missions to Mars. Hello, Richard.
Hi, Chris.
Now, I've made passing mention of a couple of them, but what are the main problems associated with powering probes in space?
Well, the primary problem is when you don't have access to the sun. So if you want to explore the more distant, cold, dark, inhospitable environments, then you need an alternative power source. And nuclear power is one of those alternative power sources. It turns out that even if you want to operate very close to the sun, you have a problem where solar panels generate a lot of heat, so they become less efficient, and therefore nuclear power can make a big difference. Other examples include surviving the lunar night or exploring dark, cold lunar craters. And certainly if you want to operate continuously day and night on Mars, travel large distances and function over a very long period of time, you need to develop alternative power sources.
So when space scientists who were working on things like the Apollo missions and those early probes were looking at those very problems, what sorts of things did they come up with as a solution? Or did they jump literally on this 200-year-old bit of physics and say thermoelectric generators is the way to go?
Well, they did essentially that. The use of radioisotope thermoelectric generators in space goes back to the 60s. The US has been very successful in launching a number of these systems in exploring the moon and exploring deep space. And Russia has been very successful in using thermoelectric generators to convert heat generated from reactors in space into electricity. Russia has launched more than 30 reactors into space.
So, in essence, you have a radioactive source, a piece of plutonium or strontium or something that radioactively decays vigorously and produces heat, and that gives you the hot side of your thermoelectric semiconductor, like we were discussing. I would guess that space, being cold as it is, 3 degrees above absolute zero, that's quite a good cold side.
It is, but it's actually quite challenging developing a system that provides you with the constant heat source, constant delta T, and allows you to radiate any of the unconverted heat into your environment without impinging on the overall mass of your radiator structure or your thermal management system that has to dissipate the excess heat. So it's actually quite challenging developing a mass-efficient system where you get a lot of power for the mass involved.
How radioactive are these sources, and how big are they? So if I have a 1-ton satellite or something, or probe, which I'm going to send off into deep space, what mass will be the generator, the thermoelectric generator, and how much radioactivity or radioactive material is in there?
If we look at the US systems, we're talking about 100 to 250 watt units. The mass efficiency ranges from about 3 watts per kilogram to 7 watts per kilogram, depending on the flavor.
But isn't that quite a lot of radioactive material?
Well, it's not the radioactive material that's the bulk of the mass. It's the whole system. So you have to take into account the fact that the radioactive material is encapsulated in a containment system surrounded by an aeroshell to allow it to survive worst-case re-entry into the atmosphere scenarios. You then have a radiator structure and all of the thermal management system that goes with it. If we're talking about a system for a European design that will have a mass efficiency of about 2 watts electric per kilo, and we're talking about 100 watts electric, and the whole system should weigh about 50 kilograms to 100 kilograms at most.
So when you're designing the systems that you are working on to send things like probes to Mars to explore the surface of other planets and so on. What do you have to do in terms of engineering in the safety? Because we've had one Russian mission that failed to leave Earth and has come back into the atmosphere fairly recently, Phobos Grunt. So what do you have to do to make sure that the radioactivity in there isn't going to pose a threat?
Well, you have to make sure that the radioactive material is completely encased in a system that will prevent the dispersal of the material, irrespective of the re-entry situation. So whether it lands in the ocean or lands on the ground, you have to also design in safety features that allow it to withstand launch pad explosions. These are all requirements that feed into a launch safety framework. The US and Russia have launch safety frameworks for launching radioactive material into space, and Europe will have the challenge of developing its own launch safety framework.
You mentioned that these units are a couple of 100 watts. That's not very much, though, is it? When you think about, my computer, just the computer is 300. So for running really quite high-end systems, that's not very much. Do they basically use the generator to charge up a battery so you then have, or a big capacitor, so you have something to give you surges of current to run energy-intense bits of equipment for short times? Is that how they work?
Well, you can use multiple units. So, for example, a mission requiring 600 watts, if your unit generates 100 watts, you would use 6 units. And you wouldn't necessarily need to use batteries. You could use them in combination with batteries. But space instruments and space systems are designed to minimize on the amount of power that they need to operate.
So what are the big challenges that you're now trying to overcome? Because we've been working on these things for 40 or 50 years, haven't we? And successfully too. So what are the big challenges that still remain to be overcome?
For Europe, the challenge is to develop its own capability in building both radioisotope thermoelectric generators and radioisotope heater units. Europe will be using an alternative isotope to what's been used in the past. So the challenge will also be to be able to produce the isotope in significant quantities.
Why do we need our own capacity? Why can't we just go to NASA and say, well, we'll borrow one of yours?
Well, there is a general shortage of plutonium production, and Europe has access to americium-241, which is in the separated plutonium in Sellafield in the UK. It would be more cost-effective for Europe to use material that is available.
Super. Richard, thank you very much. That's Richard Ambrosi. He's from the University of Leicester. And this is Chris Smith and Katani with this week's Naked Scientist, talking about the technology that could get more energy out of waste heat that we throw away at the moment and turn it into useful electrical energy. Laurie Winklis from the National Physical Laboratory is with us. We've got an email here for you, Laurie. This is from Mike Don, who says, could thermoelectric generators be used as a major non-polluting energy source with vertical pipes in the sea? In the bottom of the pipe at depth, there'll be a temperature of about 4 or 5 degrees. The top end would, of course, be at about 35 degrees. Is that enough of a temperature difference?
Yeah, with some of the really efficient generators, even a temperature gradient that small can produce power. The difficulty in this case is that you tend to want the temperature gradient across a device, which tend to be an awful lot smaller than a pipe put into the ocean. So the difficulty is actually getting the gradient across the right bit of the device, as it were. But yes, even with those temperature gradients, you can get some power output.
And then you'd have the whole of the sort of energy embodied in making a system and deploying a system like that, because often people don't think about that aspect of the equation, do they? Think, I can make a 5% saving over here, but then don't necessarily think about where do the materials to make that solar cell or whatever come from, and how much does it cost to buy those, and the carbon footprint of shipping them halfway around the world. Yeah,
the cost of life is always a big issue. So yes, you have to produce the materials, they have to be uniform enough, they have to be of good enough quality, and then they need to be implemented. So yes, there's always a difficulty with that.
We've had a question in from Graham Bartlett. I guess this is one for Andrew. And he says, could we use TEGs to generate electricity from human body heat? Because obviously we're hotter than our environment around us.
Yes, that is quite possible. The humans are, 30, 35 degrees C versus the ambient temperature of maybe 20 degrees C, 25 degrees C. So a small temperature difference is sufficient to generate a small amount of power. And as electronics gets more and more efficient, we're down at microwatt level for various things now. So yes, you could quite feasibly have a human-powered electronics using the thermoelectrics as a generation mechanism for that power.
Are you turning people into cyborgs at the NPL? Laurie?
Not that I'm aware of, but maybe my microchip's not allowing me to say it.
Hang on, you've got an iPod plugged into your leg. We've got another question for Andrew as well from Jim Robertson, who says, what about domestic gas boilers? Could we scale the technology down to a domestic level?
Domestic gas boilers, I suspect, would probably not be a particularly good use for thermoelectrics, because thermoelectrics are inherently very inefficient at the moment, maybe 5%. However, if you take something like a wood-burning stove, the primary purpose of that is to produce heat in the room. And if you covered the surface of the stove with thermoelectric material, you could pick up or generate a certain amount of electrical energy from the heat transfer through the thermoelectrics. In other words, the primary purpose of the stove is to heat the room, and the heat going through the thermoelectrics does that. But you can convert a percentage of that into electricity as the heat goes through these thermoelectrics.
Got a question here from RF Axel in Second Life. I think this is probably relevant to you, Richard. He's asking, do they use safer stuff as the isotope sources like thorium? I'm not sure. Is thorium actually any safer?
No. Traditionally, it's been plutonium-238, which has been used for powering radioisotope thermoelectric generators. Thorium is not used for such systems.
Thank you. Maybe, Laurie, you can answer this one. Android Neox, also in Second Life, is asking about oil refineries and talking about the sort of flame that you see coming off the top of the oil refinery and wondering if we could get something useful out of that.
Maybe, possibly, but you're going to have big engineering issues. If you have put something into a flame, you might have some mechanical issues. You might burn off the electrical connections and, thus defeating the purpose of putting it there.
Yeah, and is it really that much energy? I mean, it's big and visual, but it's probably a trivial amount in the grand scheme of things, isn't it?
Yes, it probably is pretty trivial.
Talking things that aren't trivial, though, just to finish us off, Jeff Brewer on Facebook, nakedscientist.com/Facebook, wonders, Andrew, what size of generating station do you need to be working with in order for the system like the one you were discussing to be cost-effective?
I would say that's an open question at the moment. If I was to really go out on a limb, I would say a megawatt would be the point at which you would have a cost-effective system.
OK, so about a megawatt, but many stations are well beyond that, so we presumably are in pretty good shape. Kat?
Yeah.
And now, weightless with excitement, here's Hannah Critchlow with a rather boozy question of the week.
The Naked Scientist's Question of the Week, brought to you in association with the Houter Wisman Foundation, supporting science and education, from alpha to omega.
This week, a question that's out of this world.
This is Björn Faller from Stockholm, Sweden. I'm an engineer by profession, but I have started some hobby-scale beer brewing. I wonder, what happens if you brew beer in 0G?
So, is it possible to brew up a bevy in space? With the answer, here's Professor Charlie Boone, Toronto University scientist who studies the yeast responsible for fermentation.
I have, in fact, sent yeast into space. So our group collaborated with NASA, and we sent yeast up in the last shuttle mission, and I can guarantee you that they grow perfectly well in space. Now, we never tried to make beer in space, but I would wager that you could make beautiful beer in space. And the reason I think you could is because if you take yeast and you mix it up in a broth with glucose, they are going to love eating that glucose, and they're going to turn it into ethanol just like they would down here on Earth. There would be a little bit of an issue where they wouldn't settle out of the beer. The gas would be mixing around, and you would have to vent off the gas as the yeast grew. And in the end, you'd have a very cloudy beer. That's what I would wager.
And Dr. Barbara Dunn, Stanford University scientist, comments,
as a yeast researcher and also as an amateur beer maker, I would say that if everything was done at the correct temperature, the yeast would grow fine and in zero gravity produce a beer. They would make the usual alcohol content and most of the usual flavors. If you were making a really big batch of beer, you'd actually have to worry about all the carbon dioxide that the yeast make during fermentation and make sure that it doesn't asphyxiate the astronauts. Finally, after the fermentation was over, I think it would be nearly impossible to bottle the beer. I think everything would go everywhere. So overall, I'd say that it probably wouldn't be the best tasting beer or the best looking beer, but it would be out of this world beer.
with that quandary resolved, we ponder the reality of superheroes and supervillains.
Hi there, my name is Julius Burke, I'm from London, and what I'd like to know is, of all the lasers employed by all of the supervillains portrayed over the years to variously destroy the world, another planet, or indeed our struggling heroes, super or otherwise, which is the most realistic, both in terms of the science behind them and the world-dominating application for which they have been chosen?
Could Goldfinger blast Bond's bits with a laser? Could a lightsaber actually work? Send your thoughts on this quandary to chris@thenakedscientist.com, tweet @nakedscientists, write on our Facebook page, or join in the debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow. Well, that's all we've got time for this week. Next week, we're going to be looking at lasers, including X-ray lasers that can probe the physical properties of matter, and a laser in a briefcase, which has been developed by researchers at Cambridge University's engineering department to take medical diagnostics on the road. If there's anything you'd like to know about that, then do get in touch. You can email me, chris@thenakedscientist.com, or tweet @nakedscientist. You can paste on our Facebook wall as well. Thank you to Laurie Winklis, Andrew Knox, Richard Ambrosi, and our production team, Tom Siemens, Ben Valsler, Mira Senthilingam, and Hannah Critchlow. Have a great evening and see you next time.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council, and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.